Today, we're going to tackle a really crucial concept in climate science, global warming potential. You can think of it as the universal ruler scientists use to compare the impact of all these different greenhouse gases. And trust me, understanding it is totally key to understanding climate policy. So let's dive right in.
So let's just start with the main problem right off the bat. Imagine you've got a gas like methane. It's super potent, but it's gone from the atmosphere in about a dozen years. Then, on the other hand, you have something like a perfluorocarbon, which can hang around for 50,000 years. How on earth do you compare those two on a level playing field? It's a real head-scratcher, and it needed a pretty clever solution.
And that solution, that clever idea, is a metric called global warming potential, or GWP for short. The best way to think about it is like a universal yardstick. It's one single ruler that lets us measure every single greenhouse gas, no matter how different they are, on the exact same scale.
Okay, so what is it exactly? Well, the official definition is that it's a measure of how much heat a gas can trap over a certain amount of time. But here's the most important part of that whole sentence, the part you really got to remember. It's all relative to carbon dioxide. GWP isn't some absolute number. It's always a comparison. You know, anytime you want to compare things, you need a starting point, right? A baseline. For GWP, our baseline is carbon dioxide. It's the benchmark that everything else is measured against. So its GWP is set at exactly 1. Simple as that.
So, if CO2 is our number one, how do we figure out the score for all the other gases? Well, it really just boils down to two key ingredients. First up is the gas's raw power to absorb heat. Scientists have a fancy term for this, radiated efficiency, but all it really means is how good that molecule is at trapping heat. The second ingredient is its atmospheric lifetime, how long it actually sticks around in the atmosphere. So you basically take its heat-trapping strength and multiply it by its staying power, and that's what gives you its GWP score.
But hold on. If gases have such wildly different lifetimes, what time frame do you even use for the comparison? To solve this, there's an international standard, and it's set at 100 years. This was kind of a compromise, right? It's long enough to see the effects of those really long-lived gases, but it's not so long but it makes a short-lived but really powerful gas like methane seem unimportant.
Now, this brings us to a super important point and a myth that we need to bust right now. A lot of people think a gas's GWP can change depending on where it's released. Let's clear that up.
So here's the deal. While the actual, real-time warming effect of a gas in a specific place might change a tiny bit based on things like altitude or what season it is, the GWP number you see on a report is a standardized global average. It's a fixed number. It's an index. Its whole purpose is to be consistent. So the GWP of methane is the same whether it comes from a cow in New Zealand or a pipeline in Siberia.
All right, now that we know how the ruler works, let's actually use it to measure the big players. And this is where things get really, really interesting.
This table lays it all out. You can see the lifetime of each gas in the middle and its 100-year GWP on the right. So check out methane, or CH4. It lasts about 12 years, and its GWP is around 28 to 36. Now, scroll down to the bottom. Look at sulfur hexafluoride. It lasts for 3,200 years, and its GWP is a mind-blowing 23,500. See? This is why GWP is so powerful. It lets us compare these insane differences on one simple scale.
And if that table didn't quite do it for you, this chart really drives the point home. See that tiny little bar for carbon dioxide? That's our baseline of 1. Then you see methane, which is about 30 times higher. But sulfur hexafluoride? Its GWP is so massive we couldn't even fit the whole bar on the screen. It just goes up and up and up. It's a fantastic visual that just screams, not all gases are created equal. So to quickly sum it up, here's the lineup. This is the clear order of potency over that 100-year window, starting from our baseline CO2 and going all the way up to the most powerful greenhouse gases we know of. And every single step up on this list represents a really big jump in warming potential. So you might be thinking, okay, that's some cool science, but why does this all matter so much? Well, it matters because GWP is the critical bridge that connects all this climate science directly to actual climate policy. For policymakers, GWP is everything. It allows a country to ask, what's better, reducing 1 ton of methane from farms or reducing 30 tons of CO2 from power plants? It helps them prioritize where to spend money and effort to get the biggest bang for their buck.
And this whole system is literally the accounting rulebook that underpins huge international agreements like the Paris Accord. It's how we're able to set and track climate targets on a global scale.
And that kind of leaves us with one final thought to chew on. Now that you understand just how huge the differences in potency can be, it brings up a really critical question for industries and governments everywhere. What's the bigger problem to tackle? A tiny, tiny leak of a ridiculously potent gas, or a massive plume of a much weaker one? The answer, well, it's not always so obvious. And that right there is exactly why understanding global warming potential is so absolutely essential.